In question 1, we want to evaluate a couple of limits. Here we have the limit as x approaches 4 of x squared minus x minus 4. Now, since this is a continuous function at x is equal to 4, we can solve the limit by plugging 4 in place of all of the x's. That is, this is equal to 4 squared minus 4 minus 4. And this reduces to, well, let's see, 4 squared is 16 minus 4 minus 4. Those two minus 4s is really minus 8. And that gives us an answer of 8 for this limit. What we have here is x squared minus x minus 4 is a continuous function, specifically at x equals 4. So we solve the limit by using this idea here. Just plug the number into the function. Can we do the same thing here? Will that work? Well, x plus 1 over x minus 1 is continuous at every number except positive 1. And here we're asked about the limit as we approach negative 1. It should be fine to put negative 1 into this function to evaluate the limit. That is, this should be equal to negative 1 plus 1 over negative 1 minus 1. The top is 0, the bottom is negative 2, and this is equal to 0. And that is the value of this limit. All right, what about this limit? The limit as x approaches negative 1 of, well, it looks really similar to part B, but this one is x minus 1 on the top and x plus 1 in the denominator. Is this function continuous at negative 1? And the answer is no, because we are dividing by 0. So if you try to put negative 1 into this function, you get, well, negative 1 minus 1 in the top. You get negative 1 plus 1 in the bottom. This is equal to negative 2 over 0. You try to type that into a calculator, it's going to say error. Now, that doesn't mean the limit doesn't exist. It just means we cannot solve it through this method. So what I'm going to do is put this function into a calculator and see what happens as we approach negative 1. So I'm going to write down the table of values that I get for that over here. So just to write down what I'm doing, in my graphing calculator, I'm entering in the function x minus 1 divided by x plus 1. I'm going to put numbers into this function listed here in the table that are very close to negative 1 just to see what values this function approaches. So to start with, I typed in negative 1 and it said error, which I already know this function is not defined at negative 1. So I'm going to put something close to negative 1. Maybe I'll do negative 1.1. So I put in negative 1.1 and it says 21. But you can get closer to negative 1, like negative 1.001. So negative 1.001. This gave me 2001. You can get even closer, negative 1.000001. Negative 1.000001. And it gives me the scientific notation of 2e to the power of 6. That means 2 times 10 to the power of 6. I can see what's happening here. The closer we get to negative 1, the bigger the values become. And it seems that that doesn't stop. We could approach it from the other side of negative 1 as well. Same thing's going to happen. We're going to get these really large values. They're probably going to be negative. But this is a way to see on a table of values that this limit, I'll say, does not exist. And the reason is, if you put numbers very close to negative 1 into this function, they start becoming infinite. And that means the limit overall does not exist. In part D, I want the limit as x approaches 0 of tangent of x plus 1 divided by cosine of x. Here we're talking about radians. All right, I think I'm just going to try plugging 0 in place of x to see what happens. Will this reduce to a number? Let's see. Tangent of 0 is 0, and cosine of 0 is 1. This is 1 over 1, or simply 1, and that means the limit does exist. I know that this is a continuous function at x is equal to 0, so I can simply put 0 into the function to get my answer. In question 2, we are solving more limits. So here we go. the limit as x approaches negative 2 of x squared minus 4 over x plus 2. We are asked to solve these algebraically, so that means, without a graph, without a calculator, through algebra. We could try putting negative 2, we could try this approach, just put negative 2 in place of the x's. And when we do, okay, negative 2 squared is positive 4. This is 0 over 0, and okay, you get error if you try that in a calculator. Now, does that mean the limit does not exist? No. The limit could still exist. It's just that this way of evaluating it did not work. So be careful here. If you put in your number and it reduces to a number that won't exist, the limit may still exist, and we can use some algebra to verify this. Okay, let's see. I think the trick that I'm going to use is I'm going to factor the numerator. So I'm going to, skip over all this stuff here. Like, this did nothing for me. But this is equal to the limit as x approaches negative 2 of, the top can be factored because it's a difference of 2 squares. And the denominator I'll just leave as x plus 2. The top is going to be an x plus x. We'll have a plus 2 and a minus 2. And that's it. That factors the numerator. The thing to point out here is that we can cancel the x plus 2 from both the numerator and the denominator. This means this is equal to the limit as x approaches negative 2 of, well, just x minus 2. Why is this helpful? This limit is equal to this limit is equal to this limit. But here is a limit where I can simply put negative 2 in place of x to get my answer. When I do that, I get negative 2 minus 2, which is equal to negative 4. So it turns out that this limit does in fact exist, even though starting by putting this number into the function, it didn't work, but that doesn't matter. That just means let's try something else. For part B, this is supposed to be, I'll just rewrite this again. This is the limit as x approaches 5 of x squared plus 2x minus 35 all over x squared minus 4x minus 5. All right, the first question is, can I simply solve this by putting 5 into all of the x's? And if I look to the denominator, if I plug in 5, the denominator is 0. So that means, okay, you'd get an error if you tried this approach. But that doesn't mean the limit doesn't exist. It may still exist. I noticed that if I put 5 into the numerator, you actually get 0 again. If you get a 0 over 0, that means you can probably cancel a common factor. So I'm going to take this problem a little bit further and factor the top and the bottom. And I'm going to see if anything cancels. All right, so for the top, it's a quadratic, and so is the bottom. So I'll set it up like this. Maybe I'll kind of partition this off here so we can ignore that first problem. Okay, so for x squared plus 2x minus 35, okay, you'd have to have an x and an x. It's got to be positive and negative because we have negative 35. The two numbers are 7 and 5. That multiplies to negative 35, yet adds to positive 2. In the denominator, again, we have to have a positive and a negative. Okay, the numbers are going to be 1 and 5. That multiplies to negative 5, yet adds to negative 4. I can cancel those x minus 5s. The original limit is actually equal to the limit as x approaches 5 of, I don't need the parentheses anymore, but this is x plus 7 over x plus 1. This function is continuous at 5. I can now put 5 into all the x's to get my answer. This is 5 plus 7 over 5 plus 1. That's 12 over 6, or 2. So the limit, in fact, does exist and is equal to 2. All right, another limit here. The limit as x approaches 4 of, okay, now we have fractions within fractions. If I check the denominator, try plugging 4 into all the x's, the denominator is 4 minus 4, which is 0. The top, this 1 over x minus 1 over 4, if I put a 4 here, I get a fourth minus a fourth, which is also 0. This makes me think we can somehow cancel a common factor between the numerator and the denominator. The way we're going to do this is by getting rid of the fractions within fractions. So a standard approach to take would be look at the two fractions in the numerator and try to get a least common denominator for them. And between x and 4, the least common denominator is going to be 4x. I'm going to try to subtract the two fractions in the numerator. To do this, I have to multiply the first fraction by 4 over 4 and the second fraction by x over x. That gives me a 4x as a common denominator within the numerator. This is the limit as x approaches 4 of, my denominator is still x minus 4, but in the numerator, I have a common denominator of 4x. This is 4 for the first fraction, and I'm subtracting off x for the second. This is how you can take the two separate fractions and add them into one. Furthermore, once you have one fraction in the numerator and a single term in the denominator, I can take this x minus 4 and multiply it into this denominator. This gets rid of the fractions within fractions. And here is what we now have. I have one fraction that has a denominator of x times 4 times x minus 4. And I have 4 minus x in the numerator. So this fraction's gone. The fraction that appears over here is this fraction because I multiplied this up to here. Technically, there's a 1 left over, but we don't need to write that. And here we are. Now, I can't put 4 into the x's. I mean, if you try, you'd get 0 in both the numerator and the denominator. So somehow, I should be able to cancel some stuff. And unfortunately, 4 minus x and x minus 4 are not exactly the same. You can't just cancel those yet. But there's a way that you can rewrite it a little bit, and it's like this. In the numerator, if you factor out a negative, well, the 4 is negative and the x is positive, and I'll write it as x minus 4 times negative 1. Right? If you multiply this negative back in, it would take you to this expression here. And I'll simply copy down the denominator of 4x times x minus 4. I did this because I'm now allowed to cancel those two common factors. And in fact, in the numerator, negative 1 is left over. This is the limit as x approaches 4 of negative 1 over 4x. This limit is equal to this one. But over here, this is a continuous function at x is equal to 4. I can now plug that number in place of x, and I get my answer. This is negative 1 over 4 times 4. And I'll write that as, well, the whole thing is negative over 16. And that is my final answer. This problem was supposed to be the limit as x approaches 9 of the square root of x minus 3 over x minus 9. Again, one that you can't solve by just putting 9 in place of x, because if you do, you get 0 divided by 0, which is an error. But that also means you can cancel some type of factor between the numerator and the denominator. When dealing with square roots, it's somehow nice to remove them from the problem. Here's a standard way to do that. We're going to multiply this fraction by 1, which won't change the value of it. We're just going to write 1 in a very particular way. So I'm just copying down the whole problem again. But instead of writing 1, I'm going to set up a fraction where I put the same thing in the top and the bottom because that will be equal to 1. But that is going to be the following. It's going to be the square root of x plus 3. So I take the term that has the square root in it, and I just switch this from a negative to a positive. When I multiply the numerators together, it's going to cancel things in a really nice way. But I also have to multiply the denominator by the square root of x plus 3 because this is equal to 1. Let me set up some parentheses. And I'm going to distribute the numerator together, but I won't do that to the denominator because eventually I would like this x minus 9 to cancel, so I'm going to leave it alone. if we look at just the numerator, this is the limit as x approaches 9 of, actually I'll start with the denominator. I'm just going to not multiply it out. I'm just going to leave it completely alone. In the numerator, we have the square root of x times the square root of x. You are squaring the square root of x, and what do you know? That gives you x. When you multiply this root x to this positive 3, you get positive 3 root x. When you now multiply in this negative 3, you get negative 3 root x. And this is the power of multiplying the top and bottom by this thing. It's going to give you two terms that cancel. Continuing, negative 3 to this positive 3 gives you negative 9. What we can do is cancel the 3 root x's. This is equal to the limit as x approaches 9 of, we have x minus 9 in the top, we have x minus 9 times root x plus 3 in the bottom, and we can now cancel that factor of x minus 9. This is equal to the limit as x approaches 9 of 1 over root x plus 3. This is a continuous function at 9. That means I can just put 9 in place of this x. And that takes me to my answer. That's 1 over root 9 plus 3. That's 1 over 3 plus 3. And I'll express that as positive 1/6. And that is the answer. All right, let's take some derivatives. Of this first one, we get 50x to the 4th minus 3x squared plus 2, and that is the answer. For this next one, I have to use the product rule, but I'm going to rewrite this as we're taking the derivative of x to the 1/2 power times e to the x. That is a first thing times a second thing. So the product rule says take the derivative of the first and multiply it by the second. Add on the first times the derivative of the second. But since the derivative of e to the x is e to the x, we're done. The derivative of arctangent is 1 over 1 plus whatever is composed in that function squared, and that means it's x squared. But by the chain rule, we have to multiply by the derivative of what's composed in the function, which is x squared. The derivative of x squared is 2x, and that is the derivative of this function. The derivative of the next function, the derivative of x is 1, the derivative of sine is cosine, and the derivative of cosecant of x is negative cosecant x times cotangent of x, and that is the answer for this one. To take the derivative of this function, I'm going to use the quotient rule, which says you take the derivative of the numerator and you multiply it by the denominator. You then reverse this. You say I'm going to subtract off, we'll leave the numerator alone, but then multiply by the derivative of the denominator. And this is all divided by the denominator squared. All right. To take the derivative of this, you could use the quotient rule, but I think it is worth rewriting this one. You know, anytime I see that root symbol, I'm really thinking, well, it really means to the 1/2 power. And I don't want that in the denominator, so I can move it to the numerator if I write it as 2x minus 4 to the negative 1/2. I've now set up the problem where I can note that this is a composition of two functions. To take the derivative, I'll bring down the negative 1/2. I'll copy down the inside. I will subtract 1 from the exponent. And by the chain rule, I have to multiply by what is on the derivative of the inside, which is 2. And that is the answer. Okay, this is now back to limits, but we're going to get our answers by using the graph of g of x. So here we are approaching negative 3 as well as 2. These negative and positives after the number means either from the left or the right. So A, B, and C seem to be closely related because we're talking about negative 3. So where is negative 3 on the graph? That's right here. So to start with, what is the limit as we approach negative 3 from the left? Okay, so that is referring to this part of the graph. As we move up the graph, we're getting closer and closer to whatever this y value is here. And I can read from the graph, well, this looks like negative 2. No other work required. Well, what about approaching negative 3 from the right, which means we're coming in from this side? So as we come in from here, we're going to this spot here, and it does appear to be at 3. The important thing about a limit is it doesn't matter what happens exactly at the point. It's the trend as you get closer and closer to negative 3. So it doesn't matter if there's a hole here or it's filled in up here. Technically, we're ignoring this one spot. We're looking at just the trend. So altogether, what is the limit as we approach 3 from either the left or the right? Well, the answer is that it does not exist. And the reason for this is it's different from the left and the right, so you can't call it just one number overall. Okay, let's see what happens in part D, E, and F, which are all related to positive 2. All right, so as we approach 2, so maybe I'll mark that on the graph, this is 2. As we approach 2 from the left, looks like, okay, yeah, we're also approaching 3. Okay. All right, as we approach from the right, the values are also getting closer and closer to what appears to be 3. So overall, does the limit as we approach 2 exist? The answer is yeah, it's equal to 3. So it's kind of like a trick, thing to look out for here, a little bit of a trick. The function equals 6 at 2, but that is irrelevant. It does not matter. The idea of defining a limit is to have something else besides talking about exactly what happens at the point. I'm going to make a note of this here. G at 2 equals 6, but this does not matter for this problem. So this does not matter. And specifically, it does not matter when you're considering the limit as you approach 2. These are different, and that's a good thing. All right, let's find the equation of the tangent line to the curve f of x equals 4x cubed minus x plus 1 at x is equal to 1. To do this, I'm going to use the following equation of a line. This is the point-slope form of the line. You need to know 2 things. You need to know a point that falls on the line itself, and you also need to know the slope. Well, the good news is the slope is the value of the derivative, and specifically when evaluated at the number 1. Now the point is going to share the x value off of this equation. So it's got to be, so x is equal to 1, and the corresponding y value is going to be on this curve. So that's going to be whatever f of 1 is equal to. This is the information that you have to basically figure out. What's the derivative at 1, and what does the actual function at 1 equal to? I'm going to start by computing, what's f of 1? This is easy. We can just put 1 into the function and go from there. So no derivatives. This is just what is f of 1. That's 4. Technically, that's cubed, but that doesn't matter. It's going to be 4 minus 1 plus 1, and that's 4. So what is our point x1, comma y1? It's the point 1, comma 4. Excellent. Now what is the slope of this tangent line? That's this thing. That means we now need to take the derivative of this function. So I need f prime of x, and I'll use that to figure out f prime of 1. F prime of x is equal to 12x squared minus 1. So f prime of 1 is equal to 12 times 1 squared minus 1, and that is 11. So great. I have the point, and I also have the slope, 11. So next, I'm just going to put that information into my linear equation. That's y minus 4 is equal to 11 times x minus 1. I mean, really, that's fine. You could leave the answer like this, but you could also write it in y equals mx plus b form. To do that, I guess you would distribute the 11. You would then add 4 to both sides. And, I mean, really either this or this is acceptable, and that's the answer. Let's find the derivative of this equation. This is implicitly defined, which means we'll have to use implicit differentiation. I'm going to differentiate both sides of this equation with respect to x. So really specifically, we're finding y prime. On the left, if I take the derivative of e to the y squared, we get e to the y squared, but we have to multiply by the derivative of y squared, and that's because of the chain rule. The derivative of y squared is 2y times y prime. Moving on. Okay, I need to take the derivative of x squared. That's simple. It's 2x. And on the other side of my equation, the derivative of cosine of y is negative sine of y. By the chain rule, though, you have to multiply by y prime. And the derivative of 2x is just 2. And technically, I mean, this is the derivative, but I mean, it'd be nicer to write it as y prime is equal to. And so next, what I'm going to do is subtract 2x to this side and add sine y times y prime to this side. So I'm going to swap those two things. I'll just note that this is going to go to the right. This is going to move to the left. The signs on them will change, but we get e to the y squared times 2y times y prime plus sine of y times y prime is equal to 2 minus 2x. We'll factor out the y prime. And actually, if I factor a y prime out from these two terms, I'll have this added to this left over. So I'm just going to say the leftover stuff's going to be this thing and this thing, since I'm taking this out and this out. It's going to be that which is divided to the other side of my equation. So this is my answer. It's 2 minus 2x divided by e to the y squared times 2y plus sine of y. And I'm not going to simplify it any further. That is the answer. Here we have a graph of y equals f of x. So no equation is actually given. Two things. I want to indicate where the derivative on this graph is equal to 0, and then I want to give a basic sketch of what I think the derivative looks like. We don't have to find any exact values here. We're just looking to get an approximate sketch of what the derivative looks like. So I don't care like how high or how low the values are. Again, this is just to get an idea of what the derivative is. So in terms of where the derivative is equal to 0, I see there's two places. There's one spot, right about here-ish that I'll mark. So like, maybe like right there. And then there's another spot, and maybe that's like right about here. Those are the two places where f prime is equal to 0. So I'm going to actually label those two places on the x-axis. When it comes to sketching a graph of the actual derivative, we're saying the derivative equals 0 here, so I'm going to put 0 on the x-axis. Same thing over here. The rest is determining where is your derivative positive and where is the derivative negative. All right, so if the derivative is equal to 0, maybe I should mark that a little bit better. if we're saying that the derivative is equal to 0, here, and we're saying it's equal to 0 here, over here, the derivative then must be either positive or negative. Within here, the derivative must be either positive or negative. And over here, the derivative must be either positive or negative. And it's up to us to figure out which is which. I'll make a couple of notes to myself. The derivative is going to be positive where the original function is increasing. And the derivative is negative wherever the original function is decreasing. The justification of this is if your graph is moving downward, like over here, that means it has a tangent line that moves downward, and any line that moves down has a negative slope. So the slopes are all negative here. The derivative is the slope. That means I want to graph negative numbers over here. So as a note, I'm just going to say, well, the derivative here is negative. That's because the original function is moving down. Now here, the graph is moving up. So that means, okay, well, the derivative must be positive here. And again, your graph, the original function, is starting to decrease again. Okay, so again, we have a negative derivative. All right, but now down here, this doesn't tell you anything about increasing or decreasing. It just tells you where the derivative is either below the x-axis or above it. So here's how I'll sketch the whole answer in. My derivative is negative, but it has to get closer and closer to this point. And that makes sense. Your graph is decreasing, which means a negative derivative, but it's decreasing less and less and less and less and less. That means those numbers are all getting closer and closer and closer to 0. So my derivative has got to go up to this point. It goes right here. From here to here, the function is increasing, so my derivative is positive. It starts becoming more and more positive because the original function is increasing more and more and more. And then it becomes less positive because it's not increasing as much anymore. And eventually it has to go back to 0. So my derivative is positive. It's more and more positive, but then it becomes less and less positive until we get back to this spot here. Over here, I want to graph a negative derivative. So here, the slopes are all getting more and more negative, and that means this is decreasing like this. So again, probably not a perfect sketch, but the idea is to understand the relationship between the derivative and the original equation. And that's it for this problem.